So once again, we want to say good evening to everybody. My name is Joe Deli Carpini. I'm the Science and Operations Officer for the National Weather Service's Boston office. And with me tonight, we have three presenters. We have Rodney, Bill, and Andrew. Bill and Andrew and myself will be giving the presentation on remote sensing, and we've called Rodney in to give us a briefing on the upcoming winter storm for Thursday and Friday, since he was in the office today, and we know how much, well, if you've been a regular, you know how much Rodney likes winter, so we like to keep him happy. So before we get started, just a reminder, you can always check our webinar page for the latest schedule or social media too. And again, our recorded webinars are on our YouTube channel. We'll be updating the schedule probably next week. So if you missed a previous webinar, go ahead and check it out on YouTube. After tonight's webinar, we'll be back on Thursday, February 25th to review the February 7th storm. That was the one a week ago on Sunday, which brought a heavy band of snow into Connecticut, Rhode Island, and eastern Massachusetts. In fact, the one band of heavy snow had snowfall rates of 2 to 4 inches per hour. And I can tell you, being under that band, that's exactly what happened. But as we head into March, we're going to be featuring more of our webinars, including event reviews. We're working on a number of them now, including the recent light icing we had this morning. But also our global weather patterns will be coming up, talking about El Nino and other kind of global circulations that dominate our weather. We'll have one on citizen science the first week of March, and that's how you can become involved with different ways in science, such as observing weather or reporting on your smartphone, things like that. We'll also be having one on extreme weather in March, and in the spring, Weather 202, which is basic weather forecasting. So Bryce is working on that, and that will be coming up in the spring. So we're going to talk about what's called remote sensing, and this is really just a way of saying observations. We have things like satellite radar, upper air observations, and surface observations. So we'll give a little bit of a background, a little bit of a history on each, and show you kind of how we use these today. A lot of this information you can obviously find online. You can always just do a simple online search or shoot me an email, and I can send you some sites to go check out if you're interested. So we're going to start off with satellite, and I believe that will be started by Bill. So Bill, go ahead and take it away.
All right, good evening, everybody. So with satellite, the one thing I was going to mention before we got into the history of it is we have two basic things that we're looking at in most of these satellite images that you're going to see here. This one here, the basic science is that what we've got is visible satellite imagery and then infrared satellite imagery, and you'll see in these different slides we go through, we're going to kind of go through the different things. Visible satellite imagery is basically on the premise of how much sun is being reflected, or how much light from the sun is being reflected, and that's what you see in the satellite image. The other infrared is basically how much energy is being emitted from the Earth, and that's what the satellite sees, and that's how we get these different images. But that's just a little bit on the basic science. There's a lot more to it, and you can, again, Joe had kind of mentioned that he's got more information on it. And you can also do a Google search and you'll find a lot about it. But let's get into the history about satellite. So the first weather satellite was TIROS-1. This is way before my time. So actually, this is one of the first times I've seen this imagery. And you're going to hear a lot of different acronyms coming up through the presentation here. So TIROS is called basically is television infrared observation satellite. It was launched April 1st in 1960. It orbited 450 miles above the Earth. Its weight was 270 pounds, and there were 2 TV cameras and 2 video recorders that pointed obviously towards the Earth. And it operated 78 days and sent 19,389 pictures. And as you can see on the right-hand side is one of the first, or the first satellite image from the satellite. So since TIROS-1, satellite imagery has gotten obviously more technologically advanced, and the satellite that we primarily use, especially at our office, is called GOES, or the Geostationary Operational Environmental Satellite. It was developed between a joint effort between NASA, or the National Aeronautics and Space Administration, and the National Oceanic and Atmospheric Administration, NOAA, in 1975. And so we're actually on GOES, I believe it's 17 now is the latest satellite. And again, in the 70s was when GOES 1 had come out. So, so I kind of mentioned earlier on with these satellites, there's basically two things that we're looking at. It's either visible or infrared. And then visible, in this instance, you can see on the image on the left here is convection that's happening, or a bunch of different thunderstorms that are occurring in southern New England. And visible satellite, what we're looking at usually is the monitoring of clouds. You can even see aerosols, smoke, dust. Sometimes when we have wildfires in the summer, you can see, the smoke coming in off of that. And then also for air quality monitoring. And now getting into the vast majority of the other things that we look outside of visible is infrared. And the thing with infrared, there's a bunch of different ways that we can look at infrared by looking at very specific energies that are coming back. And one of them is the near infrared, which is also called the veggie band. And what you can see is you can see burn scars. So if you've had a very big wildfire, that will leave a mark that that infrared can pick up. And with near infrared, land is a lot more reflective, so it's good for detecting islands, lakes, flooded regions, and land water boundaries. And as you can see here, this is you can see a really good land water cutoff in the Great Lakes region. So kind of highlighting that. Another one is the near infrared, the cirrus band, and this helps detect thin cirrus during the day, as the lower troposphere is not routinely sensed. And then also volcanic ash. And in this image, obviously no volcanoes or anything like that, but we can see some thin cirrus in the image here. Another infrared bands that we look at would show low stratus and fog, fire and hot spot detection, which you'll see an image of a little bit later, and cloud top temperatures. And then this image right here is showing different cloud top temperatures. And in this case, if you look at like when the greens are popping up offshore, that's the colder cloud tops, kind of telling us that that those clouds are a bit stronger than, or where we could have some thunderstorms. Another band that we look at is water vapor, and then since the latest GOES generation, now we have the ability to not only look at one level of water vapor. Now we can look at the lower, middle, and higher levels of the atmosphere. With those different levels, there are different things that we're looking for. When you're looking at the upper level features, we're looking at jet streams, waves, and some other different things. For mid-level features, there's mid-level feature detection, and then for the low-level feature detections, you can see elevated mixed layers, fronts, and I think in this image, I'm pretty sure, Joe, this must be a lower one because you can even see this outflow boundary coming out from. I'm gonna guess there's a thunderstorm complex in there.
Yeah, that's correct, Bill. This is a lower one.
Yep. And then one other thing that we could do with these different infrared bands is we can kind of combine them together to try to bring out different features that we're looking for. And so one of the what we call RGBs, which is like a red, green, blue, different image combination that we do, is the day cloud phase distinction. And what that does is it could show ice in the clouds, and it can identify where there's cirrus versus stratus. And then also, if you know that there's ice in clouds, especially with summertime clouds, there's the potential for producing lightning. And in these kind of images with the summer storms, when you're seeing those orange colors, that's where you're seeing more of a risk for ice. And when you're looking over, south of southern New England, that's the cirrus clouds, whereas over northern New England, that's where the thunderstorms are. And then this is just another image of the day clouds phase distinction, and it's showing where we've got thunderstorm activity over southern New England. And again, those when you're seeing those brighter oranges, that's where there's more of a risk for more ice and also more lightning. And just in comparison, a little bit different. This is what the visible satellite loop would show you. Again, still showing you convection, but you can't see really where it's really hard in this, comparing this image to the previous image, to distinguish where there's a lot of ice in clouds versus just looking at the visible. Another RGB that we use is the nighttime microphysics, and in this, what we're trying to look at usually, especially at nighttime, is low clouds, stratus, and fog. And you can see in this image, it shows up as aqua. You can see those lighter colors over northern New England and even into southern New England ahead of the higher clouds, where we've got some fog or some, that's probably more some stratus moving in. However, the limitation of it is it's only useful at night, and the thin fog can blend in with the surface, depending on what kind of temperatures we've got in the region. And then, so the bottom right-hand corner is kind of highlighting a hot spot where where there's wildfire detection, and in the top left-hand corner, that's another different kind of image, which again is showing hotspot detection, but you can even see some of the smoke, although there are two different, there's some differences between those two images, but they're basically showing the same thing. And then lastly here, we've got the GeoColor Imagery, and this basically allows us, it's kind of similar to those RGBs, where we're combining different things to pull out a satellite image. But in this, what we're doing is it includes day and night backgrounds to make a seamless transition from visible satellite during the day to nighttime infrared imagery, and you can kind of see that transition there pretty well on this GIF. And then another thing that satellite imagery that we could do with satellites is you can get derived motion wind. And what it does is it uses a set of 3 sequential images to estimate the atmospheric motion following a set of targets. And those targets typically are cloud edges or clear sky water vapor gradients. This is just showing the winds in the different levels of the atmosphere across the southeastern United States, where the white colors are up like towards like the jet stream level winds, and the green colors are going a little bit lower in the atmosphere. But another one that they'll use this for, and we don't have it on the image here, is they'll actually use it to help estimate the intensity of hurricanes from time to time too. They'll use this imagery because we can't always be flying planes into the storms when they're well out in the Atlantic or Pacific. And then the last image here, another product that we can use with our latest generation of satellites, is the geostationary lightning mapper. And on the left-hand side, you can kind of see with the visible imagery, you could see where lightning's being detected. And it's a good transition because we're going to get into radar in a little bit here. But the intensity of how much lightning that we're seeing is indicative of how strong thunderstorms are. So, and with that, we're on to radar.
All right, thank you, Bill. This is good evening, everybody. This is Andrew. We'll go ahead and move on to advance the presentation here. Looking at radar as sort of our next remote sensing topic, and that's moving forward to the history there of radar. Radar is sort of a popular remote sensing product. So that we use it every day, on air meteorologists use it as well. So some of the popular products. A little bit about the history about radar. It's an acronym that stands for radio detection and ranging. That's what radar sort of stands for. And some other sort of important points in the milestones in radar. Back in 1904, a gentleman by the name of Christian Halsmeyer developed a device that could remotely detect ships beyond visual range. And sort of moving on from there, back in 1917, famed scientist Nikola Tesla outlined how radar could be used to track ships by transmitting pulses at regular intervals. And back in the 1930s, the Allies in Germany developed a sort of a pulsing sort of radar, used again developed by the British, the French, the German, and U.S. militaries. The Allies actually thought that the Germans were developing, quote, death rays, but that's obviously not proven correct. So just moving forward here in the 1940s, the science of radar meteorology was really born. It was born during World War II. Started with a radar device that was developed by the U.S. Navy. And in 1941, a defense radar on the southern coast of England actually tracked a thunderstorm with large hail. And they tracked it over a distance of 7 miles. So that's sort of the first real sort of weather radar, remote sensing detecting weather back in 1941. And in 1943, the first operational weather radar was built in the Panama Canal Zone. So that's a little bit about just the history of radar. Now we'll talk a little bit about the different radar systems and sort of the history with that. And the National Weather Service, the first wave of radars was built in 1957, and the acronym is Weather Surveillance Radar, WSR. In this case, WSR 57 is being the year that the radars were put into the operational network. And these 1957 radars were the first ones in the U.S. There was a total of 66 of them, and they scanned at a single elevation angle, which basically is the angle that the radar is sampling from off the ground. In this case, it's half degrees, 0.5 degrees off the ground. At this point in time, you're only sensing reflectivity only. So nothing about radar velocity that we can also detect. We'll talk about that in a minute. But these radars were also, their electronics were based off of vacuum tubes, and those remained in operation until the 90s. Now fast forward about 20 years later, and we get some additional radars to fill gaps in the radar network. But there's still basically, these are the WSR 74 radars. And again, these were sort of added to sort of fill in gaps in the existing WSR set of radars. So now with this extra set, you had a total of 128 radars. Similar idea where it still scans just one elevation, and you only were looking at reflectivity products only with it. But the difference with these is that these were based on transistors in terms of their electronics, as opposed to the vacuum tubes that the older set of radars were working on. And these remained in operation as well until the 90s. And then sort of our more modern network, the Weather Surveillance Radar 1988 Doppler, or the acronym is WSR 88D. Those were all implemented across the country in the 90s. And it's not just a Weather Service effort. It's a tri-agency partnership between the National Weather Service, the Department of Defense, and the Federal Aviation Administration, where there's now a total of 160 radars. And of those, most of those are owned by the Weather Service, 122 of them, in fact. And those scan multiple elevations at different speeds. They look at reflectivity and velocity. So that's sort of the more modern version of radars that we have at our disposal. Again, these things are old, and they tend to you have to do some routine maintenance to them every now and then, and sometimes that can lead to some outages. But this is the more modern version of radar that we have at our disposal. Now, here's sort of a neat little comparison in radar coverage from the WSR 57 to 74, it's sort of like the olden days, versus the more modern radars that we have today. And you can really see what sort of sticks out comparing the two. Is that on the left, you hardly had any radar coverage really at all across the West. You also didn't have any up in northern Maine as well. But now you fast forward, looking at the current set of radars that we have now, there's a lot better coverage. There are still some gaps in coverage, especially in areas where they can't see below 10,000 feet. And that's just often because of elevation. So that really sort of sticks out in the West where you have really tall mountains. You always see below 10,000 feet with some of those. All right, so now sort of how the radar actually sort of works. So what it does is it sends out like a radio signal in a burst fashion, which we call a pulse. So what it does is the radar will listen for a return signal, depending on whatever it's hitting. When it hits the target, the power returned from the target gets sent back to the radar. And that's sort of what we see on the radar maps that we display and you have access to. And what the radar will do is basically it'll scan a bunch of different elevation angles. And once that's done, depending on the mode that it's in, that could take anywhere from 4 minutes or it can take as much as 10. It creates what's called the radar volume, where we'll be able to sort of get a sort of a vertical picture of what the radar is sampling, not just at the ground, but also well into the atmosphere as well. So we talked before, I just talked briefly just about this sort of what sort of scanning strategy it's in. We call that the volume coverage pattern, or VCP is for short. And there's two primary modes. There's a clear air mode, which is a mode that is where the radar is typically active, during basically clear air where there's not any active weather happening. So that tends to be a little bit of a slower pulse. You can sample things like birds, sort of with that. That's sort of the more traditional clear air mode. The next mode is precipitation mode. And there's a couple of VCPs with those, and those are the numbers there you send in the parentheses. VCP 215 and 212 are the two common ones. That's a little bit of a faster scanning strategy. It has more radar tilts to it that it has to scan through, but it does so at a rapid rate because you have active weather that we have to carefully monitor. And again, the VCP, what it is, it consists of the radar making several 360-degree scans of the atmosphere, and it samples in a set of increasing elevation angles until it's done, and then you get what's called a radar volume is what that's called. So as I mentioned before, there's several VCPs, but they basically can be categorized in sort of the three modes that you see here. The clear air mode, which again that takes a little longer to go through its cycle. It takes 2 minutes per elevation, and those charts that you see on the top are the elevation angles that are being sampled in each mode. So that takes about 10 minutes to complete. Fortunately, there's no active weather. That's a good mode for it to be in. Now say you have a little more on the radar, you have to watch. The radar will kick into what's called precipitation mode. That's your middle volume coverage pattern you see there. This gives you a little more elevation angles to look at. It's also a little quicker. It samples as opposed to 2 minutes per scan per elevation angle. Now it's going every minute. So it takes in Hall, it takes about 5 to 6 minutes when it's in precipitation mode. Now we have really active weather, essentially some severe storms on the radar that you have to watch. Now you're in storm mode. And in that sort of mode, the radar is sampling even faster, 30 seconds per elevation tilt. And for these, you actually can get a full volume scan out of it every 4 to 5 minutes. Whereas the lower elevations, actually, you can get those every 2 to 3 minutes, actually. And that's really helpful when you're looking to look at things like tornadoes and mesocyclones and things like that. That's where that mode becomes really, really important. So here's an example of what some of the products that we can produce from radar, or that could be generated. This is the most sort of the more familiar one. This is radar reflectivity, and this is simply a depiction of precipitation. Basically, the radar is getting all its power back from whether it be rain, if it's snow, if it's hail. It's sort of returning all that power back, and that basically the darker the colors you see, the more intense the precipitation is that's falling. And this example here was from May 15th of 2020. This was some severe storms that we had last summer. We had a line of severe storms that moved across western New England into the Springfield, Worcester, Boston areas. This is sort of an example of radar reflectivity that we have at our disposal. And again, with these, the larger and more closely spaced particles, those reflect more energy back, which leads to the higher reflectivities there. And the next one that we can look at too is radar velocity, and that's what that does is it takes the precipitation particle and it uses what's called the Doppler shift effect. You may notice, we'll say a car is, say you're standing stationary on a road, and you see a car coming past you. It sounds closer to you as the car nears you, and then as it moves farther away, the sound gets a little muffled, and you're not hearing it as well. That's the Doppler shift, and we can use that to sort of determine some of the two different products here. Basically, a base velocity product, which that just is sort of a ground relative product. In other words, it doesn't take out the storm's actual motion itself. And the way this is colored is basically the reds are the red shaded colors here. Those are away from the radar. That's what that sort of orientation means. And the sort of the greens and the blues are those are towards the radar. So when you see those in really close proximity to each other, that's usually an indication of what we call storm scale rotation. And another way we could sort of look at that, sort of in a more accurate sense, is the storm relative velocity. But what that will do is that'll take this base velocity product and then subtract out the storm's motion. So you're really getting a sense as far as what the velocity is doing with respect to the storm itself, as opposed to at the ground. And that storm relative one is the most important when you look at things such as tornadoes and mesocyclones and things of that nature. So we've had these products for several years, but now flash forward to 2012, the National Weather Service did an upgrade to its radars to what's called dual polarization capability. What that does is basically, instead of having a radar which just sent out just a horizontal pulse and returned it back, now we're able to send out pulses of microwave energy in both horizontal and vertical directions. And you may ask why that's important. Well, the nice thing is that you can look at things we've never seen before that we couldn't really sense from radar. Things like the size and the shape of targets that the radar is sensing. Before all we were getting back is just the power return. And we still get that, but we also have a sense about the size and the shape of atmospheric targets. And that's really sort of revolutionized how we look at particles, atmospheric precipitation particles. So some of these dual polarization products, or dual pol for short, The first one here is called correlation coefficient, and that's just a simple way of measuring how similar precipitation or how similar some of those values are. So in other words, for example, if you look at the image on the left, towards the bottom right, you see a lot of darker reds, sort of magentas. In that case, your correlation coefficient is really high. So in which case you have a lot of the same precipitation falling at once. Say that could be all snow, it can be all rain. Whereas you start getting more into these yellow shades, like you see in the middle of the image here, that's more of like a mixed precipitation type. It can be a different range of sizes of droplets. It sometimes can be an indication of hail. So it's really sort of a gauge as far as how homogeneous certain precipitation particles are. If they're similar, same size, same type, or if it's more of a mix. And so because of that sort of characteristic of correlation coefficient, this can help us identify what's called the melting layer, and that's more popular for wintertime applications. Say for example how this works. Say the radar is scanning through a depth of the atmosphere. Say at the top of it, say it's all snow, in which case you get mostly red-based correlation coefficient values indicating that they're all pretty much the same size and the same type of precipitation. Towards the bottom, like say towards the ground, now you're getting more like basically raindrops, in which case that's a similar idea. You're getting more those reds, indicating that pretty much they're all the same sort of precipitation type. But it's in this middle here where you get this mix of rain and snow, because, for example, in a melting layer, what will happen is that snow as it falls will melt. So you get this sort of area of lower correlation coefficient that corresponds to roughly where the melting layer is. And that's, as meteorologists, that's really helpful when you're trying to figure out, well, how low to the ground is the melting layer. And that's for detection for things like freezing rain, sort of mixing. That's where that sort of can come into play. On a plan view, sort of the radar, some example what this sort of looks like, what this melting layer looks like. It appears as what we call sort of a bright band in reflectivity. If you look at the top left image and that 4 panel on the bottom right, you'll see that there's that sort of area, that sort of reflectivity ring, where you have those enhanced values there on reflectivity. That would be traditionally the melting layer before to the dual pole era. But with the correlation coefficient values, you can see those. You can see it show up even better. That's the bottom left image there. That's where that melting layer can come into play. And the way that sort of works, again, looking at the image on the left, again at sort of around that ring, sort of on the outer edge of it, that's snow, because you're looking higher up in the atmosphere. Below it is, right in that area is basically a mix of snow and rain. And then just inside the ring and, towards the center where the radar is, that's all rain. Sort of represented there by those orange shades, or the purple shades, excuse me. Another application of dual polarization radar that we have is the tornado debris signature. Up until we had this capability, really didn't. You were sort of making inferences about tornadoes being, doing damage and on the ground. But this makes it clear. Actually, this is basically a radar's detecting actually damage from or debris from a tornado that's done damage. So this is an indication that the debris is being locked into the air. So what kind of things do we use to define a tornado debris signature? Well, first of all, if you need to have a velocity couplet, you see that in the top right, and that has to be accompanied with an area of high reflectivity. That's in the top left. Now, then we incorporate the dual polarization products. We look at correlation coefficient, and when that drops really low, typically below 0.9, but it's usually a range between 0.45 and 0.9, because with correlation coefficient, again, it shows all different kinds of either the similarity of what it's sensing, or if it's a bunch of different things. You can imagine tornado debris has a lot of different things flying around in there, so the correlation coefficient can really sort of plummet in that situation. And then another thing that will sort of increase your confidence about a tornado debris signature is if that, we'll get into more about what the differential reflectivity here is in a minute, but you want those values to be about near zero. So that's a tornado debris signature. And moving on to the differential reflectivity. Again, this is another dual pole product that we can look at, and that helps us determine basically the shape of the target that we're looking at. For example, values that are near zero, that's more, you get more spherical sort of objects. So that's more like drizzle, that's hail, that sometimes could be birds. Is typically around zero. At values like around that are positive, especially high values that are positive, you tend up getting more sort of those, like basically with those hamburger bun sort of shapes to it. In which case, that's more like that's heavy rain, that's melting hail, that's sometimes insects and birds. That's sort of where those positive ZDR values come from. That's typically sort of heavier rain, bigger drops. You start going towards negative values of differential reflectivity. That's more typically, you see those more often in the wintertime, when you have more ice crystals that are vertically oriented. Sometimes that can be helpful for thunder snow detection. That's sort of where those can sort of play a role. And with that, we'll move on to upper air observations. Thank you very much.
All right, thanks, Andrew. So now we'll move on to the last part, which are the observations, and we're combining our upper air and our surface observations. So upper air observations actually have a pretty long history, longer than radar and certainly much longer than satellites. So these go back actually to the 1700s. So in 1749, the first upper air observation was in Europe using a kite to carry along a thermometer. And then in the 1780s, actually scientists went up in hot air balloons and took along instruments for manned observations. And if you do a little online search of that, you can actually see some cases where they passed out due to a lack of oxygen when they went up to a certain height. So that became a little bit more dangerous as they ascended higher. So moving on, and 100 years later into the 1890s, kite soundings were done, where you had a kite with instruments attached to it. And in fact, in North America, the first kite sounding was taken at the Blue Hill Observatory in Milton, so right here in Massachusetts, in southern New England. Then in the 1920s, up to the time of about World War II, aircraft were being used as more and more aircraft were being developed, and the aviation industry really took off. Some instruments were attached to aircraft, and that's actually still done today. We get a number of our observations from aircraft throughout the globe. And in the early 1930s, again at Blue Hill, the first radio sonde was attached to a balloon. And that's actually what we still use today. It's called the radio sonde, and it's sent up with a helium balloon. So taking a look at our upper air observations today, these are all the locations across the country. They're launched actually worldwide, not just in the United States or North America, all at the same time. So we can get a quick snapshot of the atmosphere kind of in 3 dimensions, going from the ground all the way up to the jet stream level, 30, 40,000 feet, sometimes even higher. And that's done twice according to Greenwich Mean Time, which is the standard around the world. So it's done at midnight and noon, which for us here in the Eastern time zone is 7 a.m. and 7 p.m. in standard time. And then when we come into daylight time, it's 8 a.m. and 8 p.m. So everywhere around the globe launched at midnight and noon Greenwich Mean Time. So radio sondes, you can see that the animation here is actually Bryce from our office. This is when he was out at Spokane on a windy day. He gave us that video. They're prepared for launch in what's called the inflation building, which is what you see here on the right. And it's inflated inside, so it doesn't, accidentally take off or anything like that. The instruments here are attached. You can see the instrument package there, the parachute in orange. And then once it's launched, the data from the radio sonde is transmitted back to the ground, and the observer has a weather station here where they can track all the data and record it and send out the observation. So for us, most people know our upper air station is in Chatham, Massachusetts, and that's not done by National Weather Service personnel. It's actually a contract observer that does that twice a day. But nearby, we have the National Weather Service offices in Gray, Maine, up in Portland, Albany, New York, and the New York City office on Long Island all launch radio sondes twice per day as well. So what is the data used for? A few things. First of all, it's used for the weather models. So the forecast that you see from the computer models going out several days, this is a big part of it. They use the radio sonde launches, the upper air data. They also use data from satellites, data from aircraft, and other observations too. But the upper air observations are a big part of what goes into the weather models. So, hopefully good data going in provides us with a good forecast. They give us a look at current observations. So things like temperature, humidity, and winds through the atmosphere. So for example, in our office, if we're dealing, say, with, a winter weather situation or a thunderstorm day, we want to see, what does the atmosphere really look like? Well, this is an example of a plotted sounding from Chatham. And if you haven't seen one of these before, it's pretty simple. So height goes up on the left, and this is in our millibar levels that we kind of talk about. So 850 is roughly 5,000 feet, 700 is roughly 10,000 feet, 500 is about 18,000 feet, and so on. Temperature is in red, the dew point is in green. So you can see as you go up kind of what's going on with the temperature and the dew point. Where they're close together, you have more moisture. Where they're farther apart, you have drier air. And then on the right, you can see the wind, direction, and speed. That's where the wind is coming from. So it'd be southeast, southwest, more of a west-southwest, and a northwest wind. So it gives us a quick snapshot of what's going on above that particular location. So then we move on to surface observations, which I think most people are probably very familiar with. And this has actually a pretty long history, the longest out of all, going back to colonial times. So many people actually recorded weather in their journals. We have weather observations from people like Benjamin Franklin, Thomas Jefferson, even George Washington. Many of the colonial settlements here in New England, there were journals talking about freezes, or you've probably seen some of our weather history posts, icing over of Boston Harbor, blizzards, hurricanes in particular. So we have some idea of past weather in the colonial times through the 1700s, really, because of people's weather journals. In 1849, we had things like telegraphs starting to be developed. So the Smithsonian actually supplied weather instruments to telegraph companies and began collecting observations. And then we fast forward a little bit to 1870. That's when the present-day National Weather Service was formed within the U.S. Army Signal Service. And that was an effort to help organize these observations nationally. Instead, again, having standard observation times instead of, kind of hit or miss or inconsistent times. So, in fact, the first observation for Boston was taken in downtown November 1st of 1870, which was the first day of kind of organized weather observations in the United States. So moving on to the 1930s to 1950s, again, with the boom in the aviation industry, weather observations were needed to support that, and that even continues today. That's why a lot of the observations are taken at airports. So, for example, in Boston, it moved to Logan Airport in 1936. Hartford's observations moved to I believe it was the Brainerd Airport in 1939, and then transferred to Bradley after that. Providence was 1937, and Worcester 1955. And these manned observations continued through the early 1990s. And in fact, the photo here looks pretty old, but that was actually what you'd find in the weather office going to the early 1990s. The early part of my career, I took weather observations manually. You would literally go up on the roof of the terminal or where the office was once per hour, take a look at the sky conditions, cloud heights, cloud coverage, visibility, any present weather going on, rain, snow, fog. You had instruments here. I can actually recognize these pretty well. You had wind direction and wind speed on these two dials. You had a barometer on this dial. And these graphs were actually a ceilometer, which was a measure of the cloud height, and a wind gust recorder to tell you any wind gusts. And you can actually see a little barograph in here, which also checked the station pressure. So this was done throughout the country, hundreds of sites. There were smaller weather service offices across the region, and these were done pretty much 24/7, right up into the early to mid 1990s. And actually, here's what some of the forms look like. This on the left was an actual form from the blizzard of '78 at Logan Airport. You can see it's kind of coated up, but has things like cloud height. You can see overcast on there, and just add 2 zeros for the heights, so 900 foot overcast. Visibility, any weather, S being snow, you have blowing snow, BS, and fog. So this was in kind of the heart of the blizzard of '78. And then everything was recorded. The standard weather, things like temperature, dew point, wind direction, speed, pressure, and any remarks in here. So this was obviously a very busy day with the blizzard of '78, but it's a great example. And also from cooperative observers too, which continues today. This was from Norton, Massachusetts, and you can actually see the snowfall totals there from the blizzard of '78. It may be a little hard to see, but it looks like 21.5 inches on the 6th and 17.5 inches of snow on the 7th. So the co-op observers report 24-hour high and low temperature, as well as current temperature, any precipitation, snowfall, and snow depth. So, and any other comments they want to make. So, again, these are both continued today. The observations are now automated, and I'll get into that in just a minute. So, as we move on to the 1990s, we had a thing called ASOS, which continues to provide us observations today, and this is a picture of one. It's actually not augmented, automated surface observation system. This replaced the human observers and was installed at airports, also at many where previously they weren't 24/7 round-the-clock observations. A lot of the smaller airports had part-time observations, usually day and evening, and then were closed at night. But even today, the human observers remain at larger airports to augment the ASOS as needed. They provide information on thunderstorms, like the location and movement, snowfall, for example. So in our area, we have human observers in Boston, Providence, Bedford, also at Bradley, and in Falmouth, which is a military site. So those they provide us some extra detail to the observations. And of course, we have our cooperative observers continue to provide our observations today, as well as some supplemental networks, things like CocoRAS, which is a rainfall and snowfall network. But this is a look at the ASOS and the components for it. You can see things like the wind direction and speed, temperatures here. The wind direction and speed are up here, kind of cups. You have also pressure, visibility. It uses a set of infrared, not almost kind of like a laser type thing where it measures the return, and has a ceilometer that shoots a laser beam kind of up into the sky, and it measures the timing from when it hits the cloud and bounces back. So before ASOS, interestingly enough, there were only 3 stations that we had weather conditions for overnight. So a lot of these stations reported during the day and the evening, but only 3, Boston, Providence, and Bradley at Hartford, reported around the clock. So if you were working the midnight shift in southern New England, you only had weather reports from these 3 stations, and that was it. So made it a little bit of challenging for forecasting overnight when you didn't have the real-time observations that we have today. So nowadays we have all of these that are plotted here. You can see the temperatures are plotted from earlier today, but all of these sites are ASOS sites. So we have certainly much more that provide round-the-clock weather coverage. Now today, another part of the observation network are home weather stations. And in fact, all of these you see here are part of the one of the weather networks. People can have, if you have a weather station at home, it transmits data out and you can send it out to the world, and that helps us supplement observations, gives us a lot more coverage than we have with the automated stations. As you can see here, it's especially the populated areas here in Eastern Mass, Cape Cod, up in Hartford, Springfield, you can see, and especially down toward New York City, you can pretty much pick out the high population areas. But these really help us out when we're looking at things like rain-snow lines, for example. Really gives us the added detail that we don't have with the ASOS network. So we'll wrap up here with just some of the uses. I think these are pretty much straightforward. The primary reason is for the sport airport operations. So the air traffic controllers know which runways are they going to use because they take off and land into the wind. So having the wind observation is important. Knowing the cloud heights and visibility determines the number of aircraft that can go in and out every hour. So that's critical. If it's freezing rain or snow, then they have to do de-icing operations, runway treatments, plowing, that sort of thing. Also input to the weather models, another very important part of that, having that first, guess as to what's going on, and for forecasting too. Also, maybe the next 3 to 6 hours, where's this low headed? Where's the warm air coming in? And of course, just what's it like outside? Is it 30 degrees, 50 degrees? How do I need to dress when I head outside this morning to work or to school? And also, you can find these online in different forms. There's a coded version, which is called a METAR, and this is what's used by the aviation community. And it also is a standard kind of around the world. So this code is used here. It's used in Europe. It's used in Australia. Wherever you go around the globe, it's kind of the international standard. We can also decode them, and you can find these on our website, the decoded observations, which shows the clouds, visibility, any weather, temperature, dew point, and the wind direction. Remember, we use the compass direction, so it's where's the wind coming from. So example, O2 is out of the north and 4 knots. And also on a map. Plot a weather map with temperature and dew point in blue, wind gusts in red, the wind direction shown by the what's called the barb, as well as some of the speeds. So many different uses for surface observations, both coded and decoded. So with that, we're going to pause right here, and I'm going to have Andrew and Bill join me for any questions, and then Rodney will move on and with a preview of the upcoming storm. So let me go through. Looks like Bill answered one question already. So from Jerry, I noticed the WSR-88D seems to always be specified as Doppler. Isn't all radar based on the Doppler concept? Nowadays, yes. But some private radars, like those used maybe by TV stations, many of them are. Some of them are older radars and aren't. Certainly the WSR 57 and 74 radars were not Doppler. But yes, Jerry, pretty much a majority of them today are also Doppler radars. Now let's see. What frequency are the WSR? This is from John. What frequency are the WSR 88A series operating in? They are called S-band radars, so they're 10 centimeter wavelength. Andrew, you know about the frequency? I'm drawing a blank on that. But I know they're 10 centimeter wavelength radars, which are kind of best suited for weather detection. Some of the radars can be 5 centimeters, but that's also what happens is when it rains very hard, it's called the signal attenuates, meaning it weakens, so you don't get a good return on it. So, do you know offhand, Andrew, the frequency?
No, I know I think the wavelength is 10 is 10, like you mentioned.
Yeah, that's kind of
not
what we go. Yeah, we deal more with wavelengths, John. I'll tell you what, you shoot me an email, I can get the answer for you from our electronics crew. I'm sure they know, or I can look it up for you afterwards. So feel
Joe,
free. Yeah, unless
I
you
did
have
a
it, Bill.
quick search on it. It's 2,800 megahertz.
There you go. Okay, John, 2,800 megahertz. Thanks, Bill. I always have someone in the back doing a search for me. All right. From Beth, does someone have to change the modes manually based on the conditions? Andrew, I'll let you take that one on the radar.
Yeah, actually, that's important. That the modes are changed. That can it depends on too on the situation too. If you have if you expect maybe if you're starting off with just some shallow or lighter precipitation, all of a sudden you're starting to see thunderstorms start to develop, then yes, we can go in and manually change to again what we call that volume coverage pattern to something that would more reflective for storms. You can also adjust. There's other things you can adjust to at the radar too that we didn't really talk about, like what the rain rate is. That's more for hydrologic purposes, like flooding and stuff like that. But yes, in some cases, like if it's going from clear air mode to precipitation mode, it'll do that for you automatically once it passes a certain threshold of basically if there's certain area of coverage where it's raining. it'll flip from clear air mode to precipitation mode. So yeah, that's probably a long answer to a short question, but that's yeah.
Yeah, so there is kind of a safety net where it will switch from clear air to precip and vice versa based on some coverage, like Andrew said. But we can also override it as we need to, and certainly for severe weather, like Andrew said, we go ahead and change it based upon what we need. So good question, Beth. Another one from John: is there a plan to integrate phased array radar technology into weather detection? I guess I can take that as the science officer. So yeah, John, there is. It's several years off. I know they're doing some testing now in the plains, specifically out in Norman, Oklahoma, where a lot of the research is done. The problem is it's very costly. So I think we're probably at least a good 15 years away from it. That's why they did the upgrades. They're doing the service life upgrades to the WSR 88Ds to extend that another 20 years. But yeah, there are plans for that. It just is going to come down to funding. As to how quickly that can be implemented. But that's kind of the next generation of our radars, what's called phased array, where there's no moving parts at all. There's no dish spinning or going up and down. It's just a bunch of sensors that point straight up. So if you want more information on that, you can do a little search. Just put phased array radar, and you can find out what's going on. But yeah, that is on the horizon, John, for our next generation of weather radars. Let's see. Oh, Tori joined us tonight. He says there's a movie called The Aeronauts about a meteorologist going up in a hot air balloon. Very good. So thanks, Tori. If you want to catch a movie called The Aeronauts, look it up, and you can see people going up in hot air balloons. Let's see. From George, our friend out in Minnesota. Thanks for joining us, George. So recently, NWS radars changed dramatically in the late fall of 2020. The new version of dual pole radar is extremely difficult to use. How can this radar image be more user-friendly? Oh, because George is talking about the what's on our website now. There was a change to the radar interface that you'll find on our weather.gov web pages. And that was because of a software change that was being done nationally. So it's a little bit more difficult to use, George, and I agree with you. I think we're all kind of getting used to it. But there is, if you're interested, I may have sent it to you already, but if I didn't, please email me. There is a link, and I believe it's on our page, Andrew or Bill, you may remember, on how to actually go through and use it, kind of like a user's guide on how to best use the radar and all the different features it has. So there are definitely more features available, which is good. The interface is a little more clunky, I would think, to use than the previous one. So, George, if you're looking for more info, again, feel free to shoot me a message, and I can provide that information to you. From Melissa, were they aware of how different Boston's observations were going to be because of the effect of the ocean? Yeah, and that's still, kind of a problem today. We take the observations at Logan, which is right on the water, whereas, especially when we get snow, you'll see maybe a half inch or an inch of snow there, and then inland, even Boston Common, they're getting 5-6 inches. But you have to remember the primary reason it's there is to support the airport, not really for climate reasons. So we use it as a climate site because it has such a long-standing record back really at Logan back to 1936, and even Boston to the 1870. But they weren't intended for climatological purposes once the stations moved to airports. So that's why we use a number of, we use different networks. We use spotters, volunteers like yourselves send us your snow measurements, and that helps us paint a much better picture of the storm. Let's see, where can we go to download this data? I'm thinking observations, this is from Landon, coded or decoded form. Go to our website, weather.gov/Boston, and under, I believe, is it observations, guys? It's under that column, just above the map. And you'll see either a map of observations, you'll see a list decoded that you can go to, or just search online, like Boston METAR, it's called METAR. That will give you the coded and also usually a decoded form as well. So there's a number of places you can find that stuff, Landon. It's all out there. And let's see, from our friend Joe, his weather station also makes METAR reports. Cool. I got to find out how to do that. From Brian, we'll go through a few more here. Are there any webcams run by the NWS? Do you use webcams to supplement observations? Bill, why don't you take that one? Webcams.
Yeah, I mean, we definitely, well, I guess first, I don't know of any webcams that we have going ourselves,
Some of the offices do.
but we
I know
do.
Gray, Maine does, Binghamton, New York does. So you'll see some of them. We don't have one yet. I think we're trying to get one set up though. But go ahead, Bill.
Yeah, but we definitely do use webcams and those kinds of things to see what's going on. Because I mean, part of the issue with the automated systems that we have is they only record every 5 minutes if something changes. And with the webcams that we've got, we could see what's happening kind of closer to real time. So we definitely do use them. Especially even in Boston, there's lots of webcams looking into the city.
Yep, we're blessed with that, being in a pretty well-populated area. From Joshua, I'll throw this one to Andrew, see if he knows this. Why is radar reflectivity abbreviated with a Z?
That's a good question, Josh. So without getting into the nitty gritty math, actually the radar there's an equation that's based off of radar. For the return power, the letter is Z. So that's why it's called Z there. That's basically its return power from the radar. That's the mathematical equation that's used. The acronym for return power is Z. So that's where that comes from. And actually the measurements of reflectivity are in decibels of Z, or dBz is sort of what it's known as. But that's sort of how we answer that.
All right. Thanks, Andrew. There you go. From John, are radio sounds recovered after their use? Yes. A certain percentage are. They actually, within the package, so once the balloon bursts, it actually comes back down to Earth with the parachute that's attached to it. And if it lands somewhere, if someone finds it, there's actually a mailing package, mailing envelope inside that they can take, put the instrument in, and return it to what's our reconditioning center out in Kansas City. And a certain percentage are recovered. The ones that aren't, fortunately, these are biodegradable. So, for example, the ones from Chatham, most of them end out over the ocean. They are biodegradable and don't really present any harm to any of the sea life or anything like that, as well as ones that fall maybe in a forest or uninhabited area. They will eventually decompose. So, but there are a small number that are returned every year. And matter of fact, we had one that was launched by the Albany office. I want to say it's back in December, that actually landed in Rehoboth, Mass, and was returned to our office. So we sent that one back in. Let's see, from Robert, could there be a repeat of the 2011 tornado outbreak this year? What do you say, Andrew? I guess there's always a chance. It's a pretty rare event, an outbreak like that. It's probably once in 50, 60 years. But what do you think?
Yeah, I mean, it's been 10. I mean, practically 10 years since the 2011 outbreak. So I don't know. You certainly could never rule it out, but that was such a rare sort of combination of both winds and like a really strong instability that's I'm gonna say no, but it's not something we can necessarily like rule out of hand either.
Yeah, I mean, every year there's always a chance, but the odds are very low in this part of the country. So again, that was a once in a 50, 60-year event, in my opinion. So let's finish up a couple more, and then we'll get on to Rodney, because I know you're all waiting for the weather briefing. So from Bob, to what degree does the Weather Service use personal weather stations, and is there some criteria used to select them? We do use them quite a bit. Maybe some forecasters use them more than others, and depending on the weather situation, but we'll use it for the rain-snow line, sea breezes, things like that, smaller scale weather phenomena in particular. There's really no criteria. If your station is reporting, we can pretty much see it on our workstations or online, and a lot of them go through some sort of QC, depend on who's sharing the data. But we can find some of them stick out like a sore thumb if they're not working properly. But for the most part, they're very reliable and I think fairly widely used in our office and other offices as well. And let's see, finally from Nachiket, I hope I'm pronouncing your name correctly. Are there difficulties in seeing or sensing the jet stream upper airflows at higher latitudes, or do polar orbiting satellites aid with this? Well, there are upper air launches done at the higher latitudes, say when you're getting up near the Arctic Circle, for example. But yeah, the polar orbiting satellites actually aid with this. They provide observations usually twice a day at the higher latitudes. Again, the GOES satellites do sample there, but not as well as down toward our neck of the woods. So it's a combination. There definitely is more limited data there, but it's a combination of the polar orbiting satellite, the weather balloons, and also aircraft that fly up if they should be heading that far north. So good question. That's something everyone always thinks of. So, all right, with that, we're going to head on to Rodney's presentation. I'm going to hand it over to him. He'll give us a preview of the February 18th and 19th storm. And Rodney, I'm guessing you haven't started the event review yet, but maybe you did. I don't know. So go ahead, Rodney, take it away.
Well, thank you very much.